Hello friends, welcome back to the lecture series on applied statistics and econometrics. We are done with the core part of module 1, which is devoted to statistical methods. So, now I am going to start discussion on some special topics, and the first topic I have chosen is analysis of variance. Now, this analysis of variance is an interesting area where you will see bits and pieces of all the techniques that we have learned so far are being applied, and some scholars say that analysis of variance, or the abbreviated term ANOVA, this particular technique has been used severely in social science disciplines like psychology, education research and marketing research. So, we are only going to look at very basic models of ANOVA. ANOVA is a vast field. I am not going to give you a very broad coverage of the topic, but we are going to just look at the most fundamental ANOVA models. So, let us look at today's agenda items. So, we are going to start with a definition of ANOVA, and then we are going to differentiate between one way and n way ANOVA, and then we are going to lay out the basic assumptions if you want to conduct ANOVA, and then we will end today's lecture with basic designing of one way ANOVA. So, it was British biostatistician Ronald A. Fisher who developed ANOVA full fledged back in early part of 20th century. But even before him there were mathematicians and statisticians who used ANOVA in the context of linear regression analysis, and Laplace was one of them. But it was Ronald A. Fisher who actually worked heavily on that particular topic, this explanation or the decomposition of the variation in data set, and it was him who coined also this term analysis of variance. So, the credit goes to him. So, what does ANOVA do? ANOVA can be seen from two different perspectives. One is basically linked with the hypothesis testing that we have covered, and if you remember we talked about comparing population means across groups, and that was basically between groups. So, we had two groups in mind, and then we talked about how to compare population mean, whether they are equal or greater than or lower than the other. But you think about a situation where you have multiple population groups. So, maybe you are dealing with 4 or 5 such populations, and you are interested to make a comparison of population means across the groups. Now, if you want to apply that tool of means test, which is basically t test or the z test that I have taught you previously, then think about the complexity of the problem. So, you have to take two populations at a time and then conduct a test and then draw a conclusion. Then you take another two populations, conduct the test and then make a conclusion. But note that you can do this kind of pairwise t test, or you can compare two population means at a time, but then you will have several t tests or z tests in the process, and then how to combine? I mean, can you really draw an inference that this population means are different from each other, or at least one population group mean is different from all other group means? That you can't say from the t test or the z test that I taught you. So, ANOVA actually helps you in doing this kind of analysis. So, that is one way of looking at ANOVA, and the other way of looking at ANOVA is from the linear regression perspective, that also I have taught you. So, ANOVA is basically a tool which helps you to explain the variation in the y variable, which you can call response variable or outcome variable or your dependent variable, through the variation in the independent variables or regressors x's. So, later we will also establish the linkage between regression and the ANOVA, but for today's lecture I am going to focus on the first angle of ANOVA, which is basically comparing population means. So, now I am going to talk about what ANOVA does. So, basically ANOVA splits the observed aggregate variability found in a data set into two parts. One is called the systematic factors and the other one is called random factors. So, what do I mean by systematic and what do I mean by random, that will be much clear as we progress in the lecture. Now, there is also an alternative definition of ANOVA. So, ANOVA can be called an inferential statistical technique that assesses potential differences in a scale level dependent variable by a nominal level variable having two or more categories. So, you see this alternative definition of ANOVA actually takes care of both the angles that I have spoken a bit earlier. So, angle number 1 was of course the comparison of population means, unknown populations means, when you are involving more than two populations. So, that you can figure out towards the last part of the sentence where I am saying that having two or more categories, and the first part of this definition actually is related to the regression concept, where it is being told here that the ANOVA actually helps me to assess the potential differences in a scale level dependent variable. So, basically the scale level dependent variable I mean here a kind of continuous y that we have seen in the regression setup, and the differences is basically the variability. So, this alternative definition is more compact definition of ANOVA, as it explains what ANOVA does from two different perspectives. ANOVA could be of two types, and the first one is called one-way ANOVA, and that basically helps us to test when we encounter with 2 plus population means, and it helps us to test whether these population means are equal or not. And the second type is n-way ANOVA, and of course, you can guess that n-way means it is a general case. So, basically here in this case ANOVA determines the influence that n independent variables together may have on the dependent variable in a regression study. Now, we are going to look at some examples of one-way ANOVA and n-way ANOVA, and after that we are going to discuss one-way ANOVA at length. Okay. So, let us look at the first example. Let us assume that there is a social science researcher who is interested to analyze the students' board exam test scores, and he or she comes with a hypothesis that in a city or in a suburban area or wherever in some locality, some region, there are multiple schools, but not all the schools are equally good. So, basically there is a school effect on the students' exam performance. So, suppose he or she wants to see if the students from one of the schools consistently outperform the students from other schools. So, if this researcher has data for 3 or 4 schools from a locality, then one-way ANOVA could be helpful to him or her, because then this will help him or her to test more than 3 population means are equal or not simultaneously. Okay. So, now let me talk about the second example, and this example is going to be on n-way ANOVA, which has the regression dimension. So, here let us assume that there is a company and the company's manager or the authority, they want to know whether worker productivity or labor productivity varies across certain factors. So, one can also say that they want to compare the workers productivity based on 2 independent variables, if you want to attach this story more close to the regression concept that you have learnt earlier. So, here let us assume we are talking about 2 independent variables. Okay. So, here you have job experience as one independent variable, and second independent variable could be Note that here the worker productivity can be seen as a continuous variable. It can be measured as value of output per hours of labor input for a particular worker. That is the way you can define worker productivity. Now, in the following slide we are going to talk about the basic design of one way ANOVA. So, what is the context? So, here under one way ANOVA we are going to explain the variation of one continuous dependent variable in terms of one qualitative factor or grouping variable with 3 or more levels. And what is the objective? Well, we have already laid out the objective in the previous slide, but let me repeat again. So, here under one way ANOVA our objective is to evaluate the difference among the means of 3 or more groups. Now, note that if you want to conduct one way ANOVA you have to start with some basic assumptions, and let us now have a look at those critical assumptions. So, here we have 3 assumptions, and the first one says that you must have independent random samples for comparison of population means. Now, what do I mean by independent random samples? It means that when I draw a sample from one population, that should not have any impact on the samples that I am going to draw from the other populations. Now, we move on to the second assumption, and that is relatively simple. I have to assume that populations are normally distributed. Then comes the third assumption, and that tells us that population variances are equal, and this is basically the homogeneity condition. So, now let us have a look at these assumptions by looking at a diagram. So, now let us concentrate on the 2 panels of diagrams at the bottom of the slide. In the left hand side you see I am measuring the random variable which is the dependent variable, it is a continuous one, and I am plotting the probability density functions of that continuous dependent variable for 3 different groups. Okay. So, first we start with how to form null hypothesis. So, it is easy to begin with a null hypothesis that there is no difference between the population means. So, the population mean of group 1 which is mu 1, population mean of group 2 which is mu 2, and population mean of group 3 which is mu 3, they are all equal. Okay. So, that is basically marked here as mu 1 equal to mu 2 equal to mu 3. So, you see these 3 distribution functions, they share the same mean, and they are showing more or less same population variance as we have to assume homogeneity to conduct ANOVA. Now, let us talk about what could be the alternative scenarios through a diagram. So, here there is a diagram which is on the southeast corner of the slide, and you note that although I am assuming that my population group 1 and population group 2 they have more or less equal population mean, let me assume that they are identical. So, then I am showing that thing by mu 1 equal to mu 2, and they also have the equal variance with the standard assumptions. But let me assume that group 3 is different from the population group means mu 1 and mu 2. So, here you see that the green PDF is shifted towards left, and it is showing a lower population mean mu 3, but the variance is still remaining the same. So, variance of population group 3 corresponding to mean mu 3 is equal to the variances that we observe in population groups 1 and 2. So, this could be one alternative situation. The most extreme alternative situation could be that 3 means they are all not equal to the other. So, in that case you will see that there will be some overlap between the probability distribution functions for this continuous dependent variable, but mu1, mu2 and mu3 will lie if not way apart, but they will be different points on this horizontal axis. So, now we are done with setting the basic assumptions, and we have roughly spoken about the null and the alternative hypothesis. So, it is time to formally write down our ANOVA model. Okay. So, here in this slide we will start with the hypothesis formation first. So, from the previous slides diagram, hopefully you can imagine how we are going to frame our null and alternative hypothesis in this case. So, we are going to start with null, which says that if I am dealing with k groups, then basically I have mu1 equal to mu2 equal to mu k. So, basically all population group means are equal. Now, the alternative says that not all population means are the same. So, it implies that at least one group's population mean is going to differ from the other population group means. Okay. So, now we are going to write a mathematical expression, an equation to present our model. So, the observed response is given by Yij, where I is basically one particular group and j is basically one particular entity in that particular group. Okay. So, Yij will be equal to mu, which is the grand mean or the overall mean in the data, plus alpha I. So, that is going to be the effect of being in group number I, and then the last component in the equation is epsilon ij, that is the idiosyncratic error. So, that means that this is the error for the group member j in any particular group I, and let us assume that this idiosyncratic error follows a normal distribution with 0 mean and constant variance sigma square. So, this is very important assumption that we must make about the idiosyncratic random error. Now, note that in this model what are unknowns? So, the unknown parameters are all mu's and the error variance sigma square. So, we need to estimate them, and after we have some kind of estimates for all these mu's and error variances, then actually some related concepts can be proposed and they are very pivotal. So, in ANOVA we say that the total variation in the dependent variable y, or the total sum of squares, which is abbreviated as SST, can be split in two components. One is called the sum of squares between groups, and that is abbreviated as SSB. So, that is basically the dispersion between the factor or group sample means that we calculate from data. Now, why I am writing between slash among? Because ANOVA can also be applied to population groups, but if you have more than two, then we say that it is among the groups. Okay. And then the second component of this decomposition of total sum of squares SST is called sum of squares within groups, or the abbreviation is SSW. So, this is the dispersion that exists among the data values within a particular factor level. So, these ideas of SSB and SSW are going to be much clear as we move along in this particular lecture, and in the next lecture I am also going to show you a numerical exercise. So, hopefully then it is going to be even more clear. So, now in this slide I am going to give you a diagrammatic presentation of one way ANOVA model, and of course it is very difficult to explain every dimension of a one way ANOVA model in one diagram. So, I am going to have a representative diagram, but let us talk about this diagram and try to understand how actually ANOVA works. So, I will now start talking about that diagram, but first I am going to bring one story in front of you, so that it becomes much more clearer to understand the diagram. So, we all know that average height of human beings in our country, it is not uniform, it varies from north to south, east to west. So, do you know what is the average height of an Indian male? So, it is roughly 5 feet 5 inches, and if you go to say Punjab, Haryana, Rajasthan towards the northwest part of the, and of course Jammu and Kashmir, if you go to the northwest part of the country, you see that average height of male are much above than the Indian standard or Indian average, which is 5 feet 5 inches. So, some demographers have also found that the average height of a male in that northwest part of our country, it can reach up to 5 feet 10 inches. So, it is significantly different from the Indian average of 5 feet 5 inches. Now, if you move towards northeast, then generally you see that average height actually falls, and it is not only in the northeast, but in the eastern part of our country also, like Bengal, Bihar, Odisha, and then you move towards northeast like Assam and Manipur and all, you see that average height actually is below 5 feet 5 inches. So, it may be somewhere around 5 feet 3 inches, 2 inches. So, you see that the population average height for our country, it varies across regions. So, if you want to test whether the average height of a male in say state Punjab and Haryana and Rajasthan, and some states from the eastern side like West Bengal, Odisha and say Assam, are they different? If you want to test that thing from some randomly drawn sample, then actually you have to conduct a one way ANOVA, and to conduct that model, you have a hypothetical model in your mind first. So, you can say that well a particular person's or individuals an individual male's height can be broken down into 3 different components. Okay. So, the first component is the overall mean, which is basically the average height of a male in our country. Then there could be factor, and that factor is basically the region factor, and that is basically that alpha that I have shown you in the previous slide. So, that alpha region factor is going to have an impact on the individual, and with that factor the heights are going to change little bit both sides. So, positive, negative, or upper, lower, whatever you want to call it, in both directions it is going to impact. And not only that, there will be some personal idiosyncrasies which will also have impact on the height of a person. And what could be those idiosyncrasies? It could be the person's status in the economy or the society. So, if the person belongs to a rich or well to do family, then the nutrition that he or she is getting from his or her food is better, and that will have a positive impact on the height of that individual. But if the person belongs to lower middle class or poor family, then the person may not have that much of nutrition from food, and then that may have an impact on his height. There could be many such issues which are like personal issues, and we may not have data on these factors, and we club every sort of unknown or unseen factors under this mask of idiosyncratic or random error epsilon. So, that is basically the story. And now let us have a look at the diagram. So, here let us look at the diagram, then we will concentrate on the bullet points. So, here you see that I have a broken line which basically denotes my average height of an Indian male. So, this is the overall mean height for an Indian male from the entire country's data, and then you see I have chosen 3 different states, and I have collected random samples. So my state 1 could be say Madhya Pradesh, okay, exactly center of our country. So now of course if I assume that these different population groups have different means, if I assume, then let us assume that there will be separate symbols. So for my population group 1, which is Madhya Pradesh, I am assuming the population mean height for male is mu1. So if you look at my population group 3, you see there is a huge difference between mu3 and mu, and that is denoted by alpha 3. So that is the group effect alpha 3 for group number 3, and as you see in the case of population group 1, there is not much difference between the overall mean mu and the average for the population group 1 mu 1. So this alpha 1, this group effect is tiny compared to alpha 2 and alpha 3. So now let us going to look at the case of one particular individual who is from say my population group 3, and that individual is marked as a green circle, and you see that that person's height is above the average height of that population group 3. So the individual's height is higher than the group mean mu 3. So here I am showing you this epsilon 3j equation for this particular individual in the graph. Now what, of course this is a hypothetical picture, what could be the most extreme scenario where you can assume that there is no difference between the population means across groups. So in that case the mu1, mu2 and mu3 will all lie on that vertical broken line. So basically you can say other way around, mu1 is equal to mu2 is equal to mu3 equal to mu, the overall mean. So that is basically the most extreme case, but there could be other possible cases also where mu1 is also not lying close to that overall mean mu. So now what do we learn from this hypothetical diagram? So we observe here that the between group variation is large compared to the within group variation, because the within group variation is given by the dispersion corresponding to this bell shaped curves for each group, and you see that is fairly low. Now the second point that we can observe from this diagram is that if we now take samples from these populations, then we can expect to reject our null hypothesis, which is basically saying that the population means are equal or identical across groups. So far we have spoken about one-way ANOVA in terms of population, but population of course you cannot access entirely. So you have to draw random samples, and then based on the random samples you need to calculate certain statistics, and then based on that you have to draw inferences. So now let us see if we have access to random samples from different populations, then what type of calculations we are going to conduct. So to conduct one-way ANOVA, we have to estimate 4 things, and we will first start with estimating the grand population mean or the overall population mean mu, and for that we have to use the statistic called grand sample mean, and that is denoted here by y bar double dot. Now note that this is kind of a new notation for you. So I have used y bar to denote arithmetic mean before, but these double dots are probably a bit new, although we have spoken about similar concept in the case of contingency table, but let me explain it to you once more here. So, here double dot means that we are varying both dimensions of our data. So, both dimension means that we have here two dimensions, one is basically the group dimension which is basically I, and there is individual dimension, and that is basically denoted by j. So, here both I and j are varying, and that is why when we are computing arithmetic mean by varying both dimensions, we are talking about taking the sample mean of the entire data set. So, that is why it is called grand sample mean or overall sample mean. Now, we move down to the second item in the list, and we need to estimate individual population means mu I with sample means. So, here I introduce a similar notation y bar I dot. So, what do I mean by this? So, here you see I am fixing ith group, I am interested in deriving the population mean for the ith group. Okay. So, I have to fix one particular I, and then I have to calculate the sample mean of my variable for all individuals which are member of that particular group I. So, here I am varying over individuals which is basically denoted by j, but I am fixing I. So, that is why it is y bar I dot. Then the third in the list is the effect for group I. So, that is basically that alpha I that I have shown you in the slide. Okay. So, that is basically mu I minus mu, okay, in other words. How can we find an estimator to measure the effect for group I? So, that is basically by taking the difference between these two means that we have already calculated. Now, we move to the fourth and last item in the list, and that is basically the population errors epsilon I j. Now, we can estimate population errors by sample residuals, which is defined as E I j, and that is basically equal to the individual observations y I j minus y bar I dot. So, that is basically the individual sample mean. So, the sample residual is the difference between the individual observations and the group specific sample means. Now, we can talk about the deviation of any particular observation from the overall mean, and I am going to show you how that deviation can be broken down or partitioned into two concepts. So, here look at the left hand side of this equation in this red box. So, that is basically talking about the difference between individual observation and the grand sample mean or the overall sample mean, and you see that in the right hand side now I have two different components in two first bracketed or parenthesis items. So, here in the first parenthesis you see that I am talking about the difference between the grand mean and the group specific sample mean. So, first component in the equation is going to give us the effect for group I that we have discussed in this slide only, and now the second component is basically that E I j component. So, that is basically the sample residual component, as it is defined as the individual observation and the group specific mean. So, here I am talking about that particular group where this jth individual belongs to. So, now from this equation we can derive the ANOVA identity. So, how do we derive the ANOVA identity? So, first these individual components of this partition or decomposition formula, we can actually take squares and then we can sum over all data points of these squared items, and then that will give us the famous ANOVA identity. So, now let us have a look at that. So, here you see that expression or equation that I am showing here at the top. So, that is basically the ANOVA identity. So, in the left hand side you have this expression involving double sum. You know how the double sum is to be computed, because we have spoken about this double sum concept in the case of contingency tables and all, but let me repeat once more for a couple of seconds. So, basically here you are summing over all data points that you have. So, basically you have k number of groups to start with, and that is why the first sum ranges from I equal to 1 to k, and then within these k groups you have n1, n2 dot 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 nk number of observations in different groups. So, that is what the second sum is talking about. So, here the individual ranges from j equal to 1 to ni, which is basically the number of observations in a particular group. So, when you are taking double sum, you are basically taking the sum over the squared differences for all data points that you have. Now, this is called the total sum of squares, and now this is broken in two different components. So, the first component is the between group sum of squares, and that is basically given by SSB, and the second component in this equation or identity is basically the within group sum of squares, and that is abbreviated as SSW. So, this ANOVA identity partitions the total variation in your dependent variable y, and that partition actually is being done in terms of different groups, and this has two components in the identity or equation, and they are called the between group sum of squares and within group sum of squares. So, this ANOVA identity will now lead us to hypothesis testing. So, this ANOVA identity will now lead us to hypothesis testing, and that we will cover in the next lecture. Thank you.